Well, I'm really starting to get discouraged because I don't have any clue where this pool is. Some pool party this is. At least we're having fun with torsion, right? Why don't you give this problem a try? You probably can solve it on your own. Just remember to use our torsion formula, right? So our torsion formula says that the shear stress tau equals the applied torque T times the radius rho over J, the polar moment of inertia. So go ahead and try it out. Make sure you draw a torque diagram first and then use that formula. I'm confident you'll be able to solve it. Once again, I encourage you to pause the video here if you haven't tried this problem already, and go ahead and try the calculations, draw your torque diagram for this particular gear shaft, and then calculate the maximum shear stress. All right, when you're ready to take a look at the solution, go ahead and pick the video up right here. So I took this picture of a giant steam engine in the Tower Bridge in London. It was awesome. Bridges meets mechanical engineering. It's such a beautiful thing. And I just want you to imagine that this is the state of torque on one of these particular gear shafts. So I'm going to redraw a free body diagram of this gear shaft ACDB with the torques applied. And so that way it's more in a linear direction so that it more matches my torque diagram. So again, I'm simply just going to follow my rules. So I said that my rules say that clockwise applied torques cause a jump up in my torque diagram, and counterclockwise torques cause a jump down. And so drawing my torque diagram, I will start at 0. I have a clockwise 50 kilonewton meters torque, so that causes me to jump from 0 up to 50. That remains constant from A to C. So I have a constant 50 kilonewton meters from A to C, at which point I jump down 125. So 50 minus 125 brings me to negative 75 kilonewton meters. That remains constant from C to D. At D, I jump up 135. So negative 75 plus 135 gives me a positive 60. So I end up at positive 60 kilonewton meters. That remains constant until I get to point B. At point B, I have 60 kilonewton meters. That causes the jump down, and I end at 0. So my torque diagram started at 0 and ended at 0. So that's usually a good sign that I probably did it right. I'm also going to plug in my sign convention. So wherever I have positive torques, that indicates counterclockwise rotation of the rod. And wherever I have negative torques, that means clockwise rotation of the rod. All right, now we're interested in calculating the max shear stress. And so we're going to apply that formula tau equals T rho over J. And I just want to keep in mind that the T, the torque, I want to use the maximum value of torque from my torque diagram. So you see, like in this particular example, we had applied torques of like 125 and 135 kilonewton meters. However, there are like offsetting each other inside the system. And so my gear shaft only sees a maximum of 75 kilonewton meters. Now, when we talk about shear stress, the negative is less important. So the negative just tells us a little bit about the direction of the shear stress. But unlike axial stress, where we have positive equals tension and negative equals compression, the negative here just kind of tells us a direction. And so I'm just going to, in calculating the max shear stress, kind of take the absolute value, figure this is like the absolute maximum shear stress, so absolute value of the shear stress here. So I've got rid of the negative sign. I've converted it from kilonewton meters to newtons times meters so that I can have everything in newtons and meters, and then my answer for tau max will come out in newtons per meter squared or pascals. All right, next I need to consider C. Now C is rho max. It's just the distance from the center of gravity to the extreme fiber of the gear shaft. So if I go back up to my cross section and I drew in what C is the radius of this shaft, and that is going to be 100 millimeters or 0.1 meters. Likewise, I plug in my equation for J. J is pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. Since I have no hollow section, it's just the outer radius to the fourth, and again, 0.1 meters. I do my math here, and I can solve for the max shear stress, so hopefully this is the answer that you got when you gave this problem a try on your own. I get 47.746 times 10 to the 6th newtons per meter squared. And again, a newton per meter squared is a Pascal. So this is 47.746 megapascals. All right, I hope you followed along with that example. This was a nice way of just getting comfortable with drawing a torque diagram for a gear shaft that had multiple torques applied along the length. We were also able to identify the maximum shear stress along the length of this member. Note that the maximum shear stress was not dependent upon G, the shear modulus of the material. It was also not dependent upon the length. So when we do angle of twist, we'll need G and we'll need the length calculations. But for just shear stress, we need the torque, the radius, C, or the distance to the extreme fiber, and then we also need the area properties to calculate the polar moment of inertia, J. Good job, guys. I knew you guys would be able to solve it. Anyhow, I think I'm starting to get close to the water. Maybe it's around here somewhere. Oh no! Make sure you have your safety glasses on. Well, the pool party is a success, I think. Feels a lot better now. See you guys next time.